Um, so hi everybody. Today we'll be presenting a research paper on WebPerf. It's a tool which can be sort of used to evaluate what if scenarios over the cloud-hosted web applications. So let's begin. To start with, when it comes to building web applications, developers today have many options as to how they can architect the systems, and many popular web applications use cloud computing platforms which provide flexibility and scalability. However, with flexibility comes complexity, as we know. So, the cloud architectures for web applications can be quite complex with many different components involved. This might be virtual machines for running code, storage solutions for data, file systems for managing files, communication queues, such as SQS for passing messages between components, and many others. Um, However, each of these components can be configured in different ways with varying costs and performance characteristics. So basically, what we can say is each resource is available in multiple tiers with different prices, performances, and isolation levels. For example, we as developers might choose to, use more expensive storage that provides higher durability and faster read times, or we might opt for a cheaper solution that's quite less reliable, but helps us with cost cutting. Overall, we can say that there are a lot of choices that we as developers need to make when building web applications on the cloud, and it could be quite challenging, to balance the need for performance and reliability with the need for, to sort of keep the costs under control. So what basically happens is that these choices can significantly impact the performance and cost of a website, and it is essential to understand the trade-off between cost and performance when making these decisions. So one option that we as developers could do would be to rely on the cloud provider service level agreements, which are SLEs. But these are, not often accurate enough to predict the performance. Even if the prediction information is available, it can be difficult to translate it to end-to-end latency, which sort of requires a deep understanding of the specific application's logic and concurrency. So basically, what the authors of this paper they've done is they've presented us with a tool called WebPerf, which can help us solve the challenge of choosing the right cloud configuration for a web application. WebPerf system, sort of helps to predict how changes in the configuration and runtime conditions of a website can, affect the time it will take for a page to load from a user's perspective. To do this, what it does is it takes input such as a website, a web request, and a hypothetical what if scenario, and outputs sort of an estimate of the distribution of cloud latency for a request. This allows what it does is this allows us as developers to evaluate the potential impact of different changes and make informed decisions as to how we can optimize the website's performance. This particular tool, it uses a combination of data-driven offline latency models of various cloud APIs and the abstracted application logic to sort of calculate the total latency of a request. The key ideas behind WebPerf is to, sort of reuse the casual dependencies of compute input calls of a given request. And the second one, as we can see here, is the application independent API latency. So what the first point enables us to do is it enables us to reuse them for repeated what if in a evaluation, since the casual dependencies of compute and input output calls relatively remain stable. And coming to the second idea, which is the application independent API latency, this means that the latencies of input output calls to many cloud resources can be predicted based on certain factors such as workload and configuration parameters without needing to consider the specific application logic. Now, here's an example of different what if scenarios. So what we exactly mean by what if scenarios? So what if scenarios are like, you can say, conditions. Say I deploy an EC2 instance in US East, an AWS instance, and I decide to change it to some geographical location. Now, what would be the difference in the latency experienced by an end time user? Or say I upgrade storage tier from the most basic tier to the highest tier with the highest cost. So what would be, sort of the difference? Or say I change the input size, what would be, the effect of it? This is what this particular tool, sort of tries to explain to us. Now, coming to the key design challenges, the first and the main design challenge is that all the previous research has focused on tracking casual dependencies in asynchronous applications. But most of the modern web applications are using what we call as what we refer to as a task asynchronous paradigm, and this is something that wasn't addressed majorly in the previous works. And the second challenge here is that in implementing the idea for cloud based web applications, in the overall cloud latency, or let me rephrase it this way. The second challenge in implementing the idea for cloud-based web applications is sort of predicting the overall cloud latency by combining casual dependencies with cloud API latency models. This is difficult due to the complexity of dependencies between compute and input output calls, you can say, and as well as due to the fact that cloud API latency models are represented best as distributions instead of fixed values. Moreover, when predicting how long will it take for a web application to respond to a user request, there are many factors that weigh in and can affect the actual response time, such as concurrency limits and non-deterministic dependencies. Now, moving on. Let's get an overview of what WebPerf is. So WebPerf is a tool that helps developers, sort of improve the performance of web applications. As we just looked, it works by taking in a workload, which basically includes a web application and a set of HTTP requests. Additionally, we as developers can also provide optional hints with to help WebPerf choose accurate, latency models for the web application's workload. Now, once we have given this workload, it automatically instruments the web application using binary instrumenter, which we'll further see. And the requests in the workload are executed, which generates a dependency graph showing casual dependencies between, various compute and input output calls executed by the requests, as well as, sort of the baseline latency of various compute and input output calls for the input initial configuration, you can say. It also includes a profiler that builds empirical latency distribution of various cloud APIs under sort of different what if scenarios. And the core component that we'll be talking of would be the what if engine, which we'll be discussing further, which uses the baseline latency, dependency graphs, and online profiles, to sort of predict distribution of cloud latencies of given requests under sort of different what if scenarios. Now, as we have seen earlier, here's the architecture of WebPerf, which basically involves, binary instrumenter, a dependency graph, and also has a profile dictionary, which would be having sort of all the cloud API latencies, you can say, in a way. Yeah. So moving on next. As we have seen earlier, one of the key challenges in WebPerf is to track casual dependencies in task asynchronous application. And before we dive deep into this tab, what we call a tab, let us understand what non-blocking APIs are. So non-blocking APIs, they're sort of a non-programming interface that allows a program to continue running without waiting for, a response from a particular type of, function or service, you can say. Yeah. So instead of blocking the program until a response is received, non-blocking APIs allow the program to move on to other tasks and then return to the original task when the response is ready. And as we can see, they usually come in two major flavors. First one is what we refer to as the APM, and the second one is what we refer to as task or task asynchronous programming. This is the paradigm of non-blocking APIs that we'll be majorly focusing on. Um so both APM and TAP, you can say they have this sort of own advantages and disadvantages. APM, it's more widely supported, you can say, and can be used with older versions of .NET, but it sort of has a very steep learning curve. TAP, it's something that's relatively easier to use, but requires a newer version of .NET. So now moving on to as we can see, let us look at how tap is implemented in C sharp. So as we can see in the code here, the process request method is responsible for processing the incoming request and initiating a non-blocking asynchronous call. So async task one here, you can say it is a async method that starts the task asynchronously and returns a task object. Now, to obtain a result from an async method, the caller uses the await keyword on the task object which was returned. The use of await, sort of doesn't block the thread, but it kind of returns the thread and schedules the rest of the method as a continuation. So now that we've looked at, so now we can, now that we've sort of looked at what tap is, now let us look at what we refer to as the two commonly used abstractions in tap, which is when on and when any. So, task dot when on, when any, you can say it is used to indicate completion of before going on to when all and when any. Here's a picture showing execution trace for a single task. Now moving on to synchronizing parallel tasks or multiple tasks. As I've said, we have two abstractions. So first thing we can talk of is when any. This particular method is used to indicate the completion as soon as one of the multiple tasks sort of completes, while when all uh, sorry, I mean when all is used to indicate the completion of multiple tasks only when all of them have been completed, while when any is used to indicate completion as soon as one of the multiple tasks completes. So that you can say is the basic difference between both these abstractions. So now that we've done familiarizing ourselves with a tap, now let us see how do we actually build a dependency graph. Now any user request in a tap application requires the extraction of what we refer to as a dependency graph. Now this particular graph should include all the nodes that sort of represent both the synchronous and asynchronous compute, as well as when all and when any synchronization points that we just talked of. And the edges in the graph should indicate the sort of casual dependencies between the nodes. However, one important thing to keep in mind is that missing nodes can sort of result in underestimating the latency, while incorrect edges can cause the nodes to be executed in the wrong order. Therefore, it is quite crucial to, sort of ensure that all the relevant nodes and edges are included in the dependency graph. Now, given below is an example of dependency graph for all the three situations we've talked so far. One is for, a single task, the first one. The second task is for when all, and the third one is for when any. Now, what are the limitations of the existing solutions to extract the dependency graphs? The main issue here is that they may not provide all the necessary information and can have quite a lot of missing information. As we can see in the last bullet here, one of the citations given used in the paper, they themselves state that a dependency graph on an average missed about 182 computational nodes, 180 edges, and about 62 synchronization points. That's quite huge. So we sort of need to ensure that no information goes missing while constructing a graph. Now, how do we construct such a graph? So we can say it sort of has two steps, you can say. The first step involves capturing the execution trace by instrumenting the application binary. And then what we do is we kind of analyze the execution trace to construct the dependency graph. So now talking of dependency graphs also, we will be typically dealing with three types of nodes, which will be a start node, a end node, and a task node. Start and end nodes, they sort of denote the start and end of the request, while task nodes, they sort of represent the asynchronous API calls and other compute and input output calls. Now when we talk of edges, now say we have an edge from node A to node B. This means that it sort of represents dependency. So we can say that the node B can only start after node A starts executing or finishes its execution. Now that we've constructed the dependency graph, now let us look at how we evaluate the latency. So you can say sort of it's a three-step process to estimate the latency. The first step involves building application independent and parameterized latency profiles of various cloud APIs on offline, not online, sorry. This means that the tool collects the data on the average latency of different APIs, which can be, sort of then used to estimate the latency of a request that uses these APIs. Then comes the second step, which involves computing the dependency graph of the request, as we've looked into earlier. And finally, in the third step, what WebPerf does is it predicts the cloud latency by combining the dependency graph, the baseline latencies, and the latency profiles for the given what if scenario. This means that it sort of takes all the information it has collected and it uses it to estimate the amount of time it will take for a request to be processed and returned in the cloud environment. Yeah, that should be about it. And another important aspect that we need to talk about here is that WebPerf sort of maintains a dictionary of statistical models for different cloud API latencies. They have two different types of profiles, you can say. First one is the application independent, and the second one is parameterized latency profiling. By uh, independent profiles, application independent profiles are something which do not depend on the application, and independent profile model APIs that are not affected by the applications but may be impacted by the configurations are something we refer to as the parameterized latency profiling. Parameterized, no, I mean, you can say they depend on the workloads, parameterized profiles, and they have multiple profiles for different workload parameters. Now that we have a vague understanding of what API profiles and dependency graphs are, we can, sort of now move on to the core part of the paper, which is WebPerf's what if engine. Yeah, you can.
Okay, so what exactly is the what if engine? WebPerf's what if engine estimates cloud latency by calculating the latency distribution for each task node in a dependency graph. Then it combines them to determine the overall latency distribution of the request. It also uses profiles, API profiles, a dependency graph that we earlier talked about, and a what if scenario as inputs to produce an estimated latency distribution. Coming to the WebPerf's what if engine, WebPerf's what if engine by itself also has challenges like selecting appropriate API profiles and enforcing concurrency limits. To the profile section, to choose the right profile, checks if the node, whether the node is affected by the what if scenario and has a parameterized profile and workload hints. Otherwise, it uses the API independent profile. To enforce concurrency limits and prevent queuing latency, WebPerf modifies the dependency graph and sets a limit of N and R concurrent calls per request, where N is the system-wide limit and R is the concurrent user limit. The concurrent user request, sorry. If a task exceeds the limit, it is removed from its parent and added as a child of in-limit siblings when any method. And coming to the next slide, in this paper, the author described the method for estimating the end-to-end latency of a web request, which consists of a cloud-side latency, network latency, and client-side latency. To estimate this latency, they use a combination of end-to-end tracking and a probabilistic estimation techniques. End-to-end tracking involves instrumenting the web page and a HTTP module to match client-side request, which then corresponds to requests seen from the cloud frontend. The probabilistic estimation uses the Monte Carlo simulation to combine cloud, network, and client latency distribution to produce an end-to-end latency distribution. The author here also uses a tool called client prediction, which takes a client-side dependency graph and a latency vector as input to estimate page load time. Now coming to the optimal profiling, the biggest challenge faced by WebPerf is determining the baseline latencies for input-output calls within the target workload. One simple solution is to allocate equal time for each request, but this is not optimal as some APIs may require more sampling due to varying latencies. To address this challenge, WebPerf uses an algorithm to allocate its time budget optimally for measuring the latencies of the input and output calls in the target workload. This algorithm is similar to optimal experimenting design, a statistical method for selecting the most valuable training data points and predicting performance in a large scale analytics. This algorithm works by selecting a subset of requests from the workload and then it allocates time to them with expected latency distribution. It also then results of these measurements to refine the latency distribution and selects the next set of requests to measure. This process continues until the time budget is exhausted or the desired level of accuracy is achieved. By using this algorithm, WebPerf is able to optimize allocating the allocation of its time budget for measuring latencies in the target workload, leading to more accurate performance measurements and predictions. Now, the WebPerf tool has several components that work together to provide performance analysis and optimization for web applications. These components are implemented using different technologies and deployed as different services. The WebPerf binary instrumenter is implemented as a NuGet package that the developers can obtain and install as a site extension. The profiler is implemented as a collection of web applications that store the profile dictionary in the Azure table. This component receives the performance data collected by the instrumenter and stores it in the profile dictionary. The What If engine is implemented as a cloud service with a web interface that allows The What If engine is implemented as a cloud service with a web interface that allows developers to specify the web app workload and what if scenarios. Overall, the WebPerf tool is implemented as a collection of cloud services and client-side packages that work together to provide web application performances. Here, given below, is the third-party applications used for evaluating the WebPerf. Coming to the next slide, the authors of the study evaluated the performance of the WebPerf tool in predicting cloud latencies on six different what-if scenarios from the social forum applications. Here are the six scenarios. I will quickly tell about three of the scenarios. The scenario one involves upgrading the Redis cache used by the web application from the lowest tier, which is the standard CO, to the mid tiers, which is the standard C2. This scenario was used to evaluate the impact of the Redis cache on web application performance. The scenario 2 involved duplicating the first of the social forum web application to two different geographic locations, specifically US East and Asia East. Coming to the third scenario, it involves increasing the amount of data read and written from the web applications to the backend blob storage to 6 MB. And here the author found that WebPerf was able to accurately predict the cloud latencies in all of these scenarios with median relative errors of less than 10% and maximum errors of less than 20%. They also conducted similar experiments for other applications and found that WebPerf was able to predict cloud latencies accurately for a wide range of applications and scenarios with the median relative error of less than 7%. Now we look at the graphs in the next slide. We have predicted latency and ground truth latency. A predicted latency here refers to the estimate of the amount of time it will take for a request to be processed. C is the actual amount of time it takes for the response to be received. And here the what if scenarios refer to different hypothetical situations that could affect the latency of the social forum. As we can see, the distributions of social forums projected and actual latencies under different what if scenarios. Here they are quite similar to each other. Hmm, And next, we try to evaluate the end to end latency prediction. In a study evaluating the effectiveness of WebPerf in predicting end to end latency, ground truth end to end latencies were obtained by accessing the index page of various applications in a Chrome browser from California. The study here is based on a cloud application hosted in the Azure US West data center, where the network RTT distribution between the client and server as the network latency. Here, the result showed that WebPerf predicted error for all applications and scenarios was small, with a median error of less than 7%. This suggests that WebPerf can effectively predict end-to-end latency with a good model for network latency between the client and server, and the web prophet-like tool can predict client-side latency. Additionally, the study found that WebPerf end-to-end prediction was slightly more accurate than the cloud-side prediction, as client-side prediction more and morely relies on baseline HTTP request latencies only, and hence it is more accurate. While offline cloud-side latency profiles have higher uncertainty than baseline latencies. Coming to the next slide, the accuracy of WebPerf prediction is affected by several factors, including the complexity and the dependency graph, the variability of latencies, and the application independence of the profiles. In general, we can say that the WebPerf is more accurate when the dependency graph is small and the latency profile is less variable and mostly application independent. For example, the Contact Manager app has a simple dependency graph which makes its prediction more accurate. On the other hand, the social forum has a highly complicated dependency graph, but its baseline is morely dependent on profiles which have the least variability, which helps the WebPerf generate a better prediction for it. Next comes the profilability. In here, the scenarios with higher variability in latency profile results in higher prediction errors. Another important factor to consider here is the application independence of the profiles. While most APIs in the evaluated applications were application independent, some apps like Contoso Ads and Course Manager use expensive SQL queries on medium-sized tables, which resulted in latencies that change as tires change. Using baseline latencies as estimates for such scenarios resulted in large errors. This problem can be avoided by using workload hints, which can provide more accurate estimate of the latencies for such scenarios. Now, the next question that we tend to face is that we can how and whether we can increase the prediction accuracy. The answer to is yes. In some cases, WebPerf prediction can be improved with the help of workload hints from developers. Workload hints are the hints which provide information about the specific characteristic of the workload that may affect the latency of an application. For example, in the case of Course Manager, WebPerf has a large prediction error when making join queries on a medium-sized SQL tables because baseline latencies are not good estimates across tiers for large tables. However, with workload hints on specific queries and table sizes, WebPerf could reactively build profiles for given queries and table size and lower the error to 4.6%. In other cases, such as with the Azure CDN's data access API, latency distribution can be highly bimodal due to item popularity. WebPerf can combine these distributions using Monte Carlo simulation and reduce prediction error to 3.2%. Lastly, in the case of social forum, considering the what if scenarios of sharing a table into two, WebPerf's prediction algorithm assumes that sharding will result in half of the load on each, but this assumption may not always hold. Without workload hints, WebPerf's estimation has a median error of 90.1% for a highly skewed workload where all the requests are accessed from one shard. However, the that the workload is highly skewed towards one shard, prediction became more accurate with a median error of 5.9%. And the author of this paper also presented us with some additional results. They considered several factors, including the impact of the concurrent limits, sources of prediction errors, the impact of measurement optimization, and the overhead of WebPerf itself. The evaluation found that WebPerf was able to accurately predict the impact of concurrency limits on performance with a median error of 2.1% when considering the limits and a median error of 87% when ignoring them. The tool was also found to have a very small error rate when predicting latencies with an average error of 0.4% across all requests. This suggests that the tool predicted latency could be improved further by using sophisticated models or just more data. The evaluation also found that the measurement optimization algorithms used by WebPuffs were effective with the optimization algorithm and collecting more data for APIs with high latency variability and achieving significantly better accuracy than the baseline schemes. The overhead of WebPerf was found to be lightweight with an average instrumentation time of 3.1 seconds and a runtime overhead of 3.3%. The prediction algorithm's operation on the distribution was found to have a moderate overhead with an average prediction time of 5.6 seconds. Overall, the results demonstrate that WebPerf is an effective tool for predicting the performance of web application and that its overhead is reasonably given and reasonably gives the accuracy of its predictions. The paper here, WebPerf Evaluating What If Scenarios for Cloud Hosted Web Application, proposes a tool that has several advantages, which includes the cloud agnostic. The tool is designed to be cloud agnostic, which means that it can be used to evaluate the performance of the web applications across different cloud platforms. This is significant this is a significant advantage for users who work with multiple cloud providers or who may need to switch cloud providers in the future. It also has and uses the real-time performance evaluation. The WebPerf tool is designed to provide real-time performance evaluation, which allows us to monitor the performance of their web application as they are running. This is significant advantage for who need to quickly identify and address performance issues to ensure that their web applications are running smoothly. Then it has the scalability. The WebPerf tool is going to be scalable, which means that it can be used to evaluate the performance of web applications of different sizes and complexities. This is a significant advantage for users who work with large, complex web applications that may require more resources to evaluate. And then comes the flexibility. The WebPerf tool is designed to be flexible, which means that it can be customized to meet the specific needs of the different users. This is a significant advantage for users who may have unique performance evaluation needs or who may want to customize the tool to work with different cloud platforms or web applications. However, it also has a few drawbacks that this paper has too, which are the complexity, unpredictability due to simulated workloads, the data privacy, evaluation metrics. The complexity here is the WebPerf tool proposed in the paper is relatively complex and it also requires a significant amount of setup and configurations to use. This complexity may limit the tool's accessibility to users who do not have a technical background in the web application performance. And coming to the unpredictability, the paper evaluates the performance of the web application using simulated workloads, which may not accurately reflect real world usage patterns or the traffic. Coming to the data privacy, the paper does not address the issues of the data privacy when evaluating web application performance. The use of sensitive data in performance evaluations may pose a risk to user with privacy and security, which may limit the applicability of the tool in certain scenarios. And lastly, the evaluation metrics. The paper focuses on limited set of performance metrics such as response time and throughput, which may not capture the full range of factors that impact web application performance. Additionally, the paper does not consider the trade offs between different performance metrics or the impact of changes in one metric on other aspects of web application performance. Overall, we can say that while the WebPerf tool proposed in the paper has potential, there are also several limitations in areas for improvement that should be considered. Addressing these drawbacks may help to increase the tool's accessibility, practicability, and applicability to real world scenarios.
So yes, that should conclude our presentation. In this paper, we were presented with a tool called WebPerf, as we've already discussed. It's something that helps us as developers to choose the right configurations, the right components, and the tiers, while simultaneously balancing performance and cost issues. We've also talked of its implementation, which mainly depends on a what if engine and the dependency graph that it's extracting. So this particular paper, presented most of its results for, 6 web applications, mainly over Azure. But most of the results that we presented were for one particular application called Social Forum. It is also, you can say it sort of automatically captures the dependencies of input output calls as well as the compute components in the request pipeline. Uh, Overall, we can say that it's a beautiful tool which can be used to sort of predict the cloud side latency. Also, the paper, I mean, the authors have also provided us extensions to sort of estimate the end-to-end latency. As my partner said, though there are several advantages, it comes with its own set of disadvantages, which we have personally felt that the paper needs to address. So yeah, that should be it. Thank you.